Every single day, your body produces about 180 liters of a fluid that is essentially identical to urine.
Yeah, which is just a staggering number when you actually think about it.
Right. Just picture that volume for a second. That is roughly 12 times your entire blood volume.
Exactly.
Your body is just churning through this massive liquid payload, hour after hour. Yet somehow, you only actually pee out about 1% of it.
Which is a good thing, or we'd be in serious trouble.
Definitely. Welcome to the Deep Dive, everyone. Today, we're taking a massive stack of medical and physiology sources to look at exactly how your kidneys balance fluids, specifically focusing on, water and electrolyte control.
Yeah, it's a fascinating topic.
And our mission today is to completely shatter this lingering 19th century myth that your kidney is just this passive little coffee filter catching waste. We want to show you the high-energy, multi-hormone engineering marvel that is actually keeping you alive.
I love that framing because to really appreciate just how hard that marvel is working, we kind of need to look at the baseline definition of what it actually means to be in balance.
Right, let's start there.
According to the medical text we pulled from, renal fluid and electrolyte balance is basically the process of holding the body's internal fluids inside a remarkably narrow, almost microscopic physiological range.
And what's the main target they're aiming for?
The main target the kidneys are trying to hit is your plasma osmolality.
Okay, plasma osmolality. Let's break that down.
Yeah, so that's basically the concentration of dissolved particles. So the salts, the sugars, the proteins floating in your blood. The kidneys are trying to pin that concentration exactly between 275 and 295 millismoles per kilogram of water.
Wait, stop right there. Because reading, 275 to 295 millismoles in a textbook is one thing, but it doesn't give me any intuitive sense of what that actually feels like.
Sure, yeah, it's just numbers.
Right. Give me a real-world anchor. Like, how salty is 295 millismoles?
Okay, think of a standard sports drink. If you look at the fluid inside that plastic bottle, it has an osmolality of around 300 millismoles.
Oh, wow.
Yeah. And ocean water, by contrast, is massively concentrated, usually sitting well over 1,000. So your blood is being carefully, relentlessly pinned just slightly below the saltiness of a Gatorade.
That is an incredibly tight window to maintain.
It really is a precarious tightrope.
Yes.
Because you are constantly messing with that balance, right?
I mean, all day long.
Exactly. You drink 3 cups of black coffee, you eat a heavily salted pretzel, you sweat through a 2-hour workout, you forget to drink water on a long flight.
Right. The inputs and outputs are just chaotic.
Absolutely. And despite all of those wild swings in intake and loss, the kidneys have to maintain your blood volume, regulate your blood pressure, and keep key ions like sodium, potassium, calcium, and bicarbonate perfectly dialed in.
So it's doing a lot more than just filtering.
Oh, so much more. The kidney isn't just a filter at all. It's a vital endocrine organ. It even produces its own hormones, like erythropoietin, to tell your bones to make more red blood cells.
Okay, so let's get into the actual mechanics of how it pulls this off. Because the transition in our understanding from, dumb coffee filter to high-energy recycling plant really hinges on that 180 liters fact I mentioned at the start.
Yeah, that's the core of it.
Because the strategy outlined in these sources is bizarre. It essentially boils down to filter absolutely everything out of the blood and then desperately claw back what you need.
The sheer scale of the operation defies logic until you dig into the physics of it. You have roughly 2 million microscopic filtering units, which are called nephrons, split between your 2 kidneys.
2 million.
Right. And the blood flows into them, and they push out those 180 liters of raw filtrate every single day.
I just can't get past the inefficiency of this design.
It seems backwards, right?
Totally backwards. If I want to clean my house, I don't throw my couch, my TV, and all my clothes out onto the front lawn,
right?
Sweep the empty living room, and then carry 99% of my furniture back inside.
No, you just take out the trash.
Exactly.
Yeah.
Why wasn't the body just evolved to filter out the exact 1 or 2 liters of waste it wants to get rid of? Why do the accounting backward?
Well, the body is willingly trading massive amounts of energy for extreme real-time precision. To run this bulk filtering operation, the kidneys consume an astonishing 20 to 25% of your body's entire resting oxygen supply.
Wait, per gram of tissue?
Yes, per gram of tissue. They are burning energy at a phenomenal rate. But that energy expenditure, buys adjustability.
Yeah, so.
Well, by pushing all the fluid out of the blood and into the tubules, the kidney can then tweak the reabsorption process segment by segment, molecule by molecule.
Oh, I see.
Yeah. So if you suddenly eat a potassium-heavy banana, or say you need to urgently hold on to sodium because you're bleeding, the molecular machinery is already in motion to make that micro-adjustment instantly across that 180 liters of fluid.
So it's faster than waiting for the blood to circulate through a slower, targeted waste removal system.
Exactly. It's real-time control.
It's brute force precision.
Yeah.
But I was really surprised to read in the sources just how fiercely scientists fought over this concept.
Oh, the debates were vicious. Back in 1844, there was a German physiologist named Karl Ludwig who proposed that the kidney used simple hydrostatic blood pressure to bulk filter fluid, just like we're describing.
But people didn't buy it.
The biological community hated it. It sounded too much like plumbing, you know?
Yeah.
Too much like pure physics.
Interesting.
The dominant view, which was championed by an English surgeon named William Bowman, was that the kidney relied on vital secretion. Basically, that the kidney tubes were just actively finding waste molecules and spitting them into the urine, leaving the good blood behind.
And it took 80 years to finally prove Ludwig right.
Yeah, a long time.
The paper from the 1920s by A.N. Richards at the University of Pennsylvania is practically science fiction. To prove the kidney filters everything and then reabsorbs it, he invented a technique called micropuncture.
It's unbelievable what he did.
He literally took a microscopic glass pipette, steadied his hands, and inserted it directly into a single microscopic nephron of a living frog to extract the fluid.
Which is just a staggering feat of manual dexterity. And when Richards analyzed that fluid, he found it contained glucose, amino acids, all the good stuff.
So it wasn't just waste.
Not at all. It was basically blood plasma minus the big proteins. He proved definitively that the fluid starts out full of valuable nutrients, and the kidney spends all its metabolic energy frantically pulling the water and salts back before it hits the bladder.
Okay, wait. If the kidney is actively pulling 178 liters of water back into the blood every day, that requires a massive physical force.
Right.
Water doesn't just move on its own because you ask it to. You need a mechanism to drag all that fluid back across the cell membranes. What is actually doing the pulling?
Well, water almost always follows salt through osmosis. So to move that sheer volume of water, the kidney utilizes a specialized microscopic structure called the loop of Henle.
A loop of Henle.
Yeah, it's this hairpin tube that plunges deep into the center of the kidney and then loops straight back up. And in 1951, scientists finally figured out how this loop works, proposing a model called countercurrent multiplication.
Okay, I have to admit, when I hit the phrase countercurrent multiplication in the reading, my eyes totally glazed over.
It's a dense term.
It sounds like an advanced calculus theorem, not human biology. How does a U-shaped microscopic tube multiply anything?
Let's break down the physical mechanics. Imagine this hairpin loop. The fluid flows down the descending limb, hits the bottom, and flows back up the ascending limb.
Okay, simple enough.
But here is the trick. The biological walls of these two limbs have entirely different properties. The descending side going down is highly permeable to water, but it completely blocks salt from moving.
Got it. Water can leave, salt can't.
Exactly. Now, the ascending side going back up is the exact opposite. It is completely waterproof, but its walls are packed with molecular pumps that actively shove salt out of the tube and into the surrounding kidney tissue.
Okay, let me see if I can visualize this properly. Imagine a factory floor with two long conveyor belts running side by side but in opposite directions.
Like this.
The workers on the ascending side are shoveling massive amounts of salt off their belt and tossing it over the barrier into the space between the belts.
Yes.
But the space between the belts is a closed room. So the salt is just piling up on the floor.
Keep going. That's exactly the physical dynamic.
Right, so you have this ever-growing mountain of salt piling up in the middle. And because the down belt, the descending side, is full of holes that let water through, all the water on that down belt feels the osmotic pull of that massive mountain of salt next door, and it gets sucked right through the holes and out of the urine.
Spot on.
Because the belts are constantly moving in opposite directions, you are trapping the salt at the U-turn and multiplying the concentration endlessly.
That is exactly how countercurrent multiplication works. You build a biological salt trap. That traffic jam of salt at the bottom of the loop creates a tremendous osmotic vacuum.
And how concentrated does it get?
In humans, it builds up a concentration gradient in the deep kidney tissue of about 1,200 milliosmoles per kilogram. Going back to our earlier numbers, that is 4 times saltier than your blood.
Wow. 4 times.
Yeah. That massive 1,200 millismol pile of salt is the physical engine that sits there, radiating osmotic pressure, just ready to suck water out of the urine and back into your body.
And if 1,200 milliosmoles is impressive, we absolutely have to talk about the kangaroo rat. This animal blew my mind.
Oh, the kangaroo rat is incredible.
It's a tiny desert rodent mentioned in our sources, and it basically never drinks free water. It survives its entire life just on the microscopic trace moisture found inside baked desert seeds.
And their survival entirely comes down to the architecture of their loops of Henle. Their loops plunge proportionally much deeper into the kidney tissue than ours do.
So they have a bigger salt mountain.
A massively bigger salt mountain. If our salt mountain maxes out at a concentration of 1,200, the kangaroo rat pushes its gradient to a staggering 6,000 to 9,000 milliosmoles per kilogram.
That's insane.
Their urine is so highly concentrated, it's practically a solid paste. Their kidneys generate such a powerful osmotic vacuum that they extract almost every single stray drop of water back into their bloodstream.
But this brings up a massive logical gap for me.
What's that?
The loop of Henle is a physical structure. It's always running, always building that massive pile of salt, just sitting there with all this potential energy to pull water back.
Yeah.
But how does the kidney know when to actually open the gates and use that vacuum?
Right.
Like, how does it differentiate between me chugging a gallon of water where I need to pee it out versus me wandering in a desert for 2 days where I need to save every drop?
That brings us to the hormonal remote controls. The primary master switch for water is a hormone called antidiuretic hormone, or ADH, which is also known as vasopressin.
Okay, ADH.
Deep inside your brain, you have specialized cells that act as salt sensors. They constantly monitor the osmolality of your blood. If your blood starts getting a little too salty, say you're sweating in the sun, your pituitary gland releases ADH into your bloodstream.
And where does it go?
ADH travels down to the kidneys and issues a very specific command to the final collecting ducts: open the gates.
But how does a hormone actually let water through? The kidney cell membranes are made of lipids, right? Fats.
Yes, exactly.
And basic chemistry tells us oil and water don't mix. Water molecules shouldn't be able to easily pass through a fat barrier, no matter how hard that salt mountain is pulling on them.
This was one of the greatest mysteries in physiology for decades. Scientists knew water was rushing across these membranes incredibly fast, but they couldn't find the physical doors.
It's like a magic trick.
Right. It wasn't until 1992 that a scientist named Peter Agree finally discovered them, an achievement that actually won him the Nobel Prize in chemistry. He found specialized proteins called aquaporins.
Aquaporins. Water pores.
Exactly. They are microscopic turnstiles embedded in the cell membrane that only let water molecules pass through, single file.
That's wild.
What ADH does is act like a chemical remote control. When ADH binds to the kidney cell, it triggers the cell to suddenly insert millions of these aquaporin turnstiles directly into its walls.
And boom, the water can flow.
Instantly, the membrane becomes permeable. All that water in the urine feels the violent pull of the salt mountain, rushes through the aquaporins, and gets reabsorbed into the blood.
And when that remote control breaks, the consequences are incredibly dramatic. The sources talk about a condition called diabetes insipidus.
Yeah, that's a rough one.
Now, when most people hear diabetes, they immediately think of blood sugar and insulin. But diabetes insipidus has absolutely nothing to do with sugar.
No, it is purely a failure of the water balancing system. It happens when your brain either stops producing ADH or your kidneys suddenly stop listening to it.
So the gates stay shut.
Without ADH, those aquaporin turnstiles never get inserted into the membrane. The gates stay locked. So even though the loop of Henle has built up a massive salt mountain pulling on the water is physically trapped inside the waterproof tubule.
It just flows right on past.
It just flows right on past and out into the bladder. A person with untreated diabetes insipidus can produce 15 to 20 liters of highly dilute urine every single day.
And the history of the name is wild. Before modern blood tests, physicians had to figure out why a patient was peeing constantly. And the diagnostic tool they used was, well, their own taste buds.
Yeah, not the best part of medical history.
They would literally taste the patient's urine. If it tasted sweet, it meant the kidneys were spilling glucose. That was diabetes mellitus, coming from the Latin for honey sweet.
Right.
But if it tasted like absolutely nothing, just pure water, it was diabetes insipidus, literally meaning tasteless or bland.
It's a very visceral piece of medical history, but ADH is only half the puzzle. ADH only controls pure water.
What's the other half?
To truly manage your blood volume and, by extension, your blood pressure, the kidney has to actively manage the total amount of sodium in your body. And for that, it uses an entirely different, incredibly complex cascade called the renin-angiotensin aldosterone system, or RAAS for short.
This is the system that seems to govern almost all modern blood pressure treatments. But looking at the cascade in the textbook, it's a dizzying chain reaction. Walk me through how it actually works mechanically.
Okay, inside the kidney, there are specialized cells hugging the incoming blood vessels. They act as microscopic barometers, constantly feeling the physical stretch of the vessel wall.
So they're feeling for pressure.
Right. If your blood pressure drops, maybe you're bleeding or severely dehydrated, there is less stretch. The barometer cells panic and release an enzyme called renin into the blood.
Okay, renin.
Renin acts like a pair of chemical scissors, chopping up a protein to create a molecule that eventually becomes angiotensin II.
And angiotensin II is the heavy hitter.
It is incredibly powerful. First, it causes your blood vessels all over your body to physically clamp down, instantly increasing pressure.
Much like squeezing a garden hose.
Exactly like that. But second, it travels to your adrenal glands and orders them to release a hormone called aldosterone. Aldosterone goes straight back to the kidney and issues a command to the cells: build more sodium pumps.
Just on demand like that.
Yep. It literally forces the cells to manufacture new protein channels on the fly, grabbing sodium out of the urine and throwing it back into the blood. And because we know water always follows salt, retaining that sodium drags a massive volume of water with it.
Powerfully increasing your total blood volume and raising your blood pressure back up.
Exactly.
Which explains why millions of people take ACE inhibitors. If you look at a common blood pressure drug like lisinopril, the ACE it's inhibiting is the exact enzyme that creates angiotensin II.
That's exactly how it works.
By taking that pill, you are throwing a chemical wrench into the kidney's RAAS cascade. You block the angiotensin II, you block the aldosterone, the kidney dumps sodium instead of keeping it, and your blood pressure stays low.
But physiology rarely relies on a system with only one direction. The kidney doesn't just need to know how to save volume, it needs an emergency valve for when you have too much volume.
Right. What if your blood pressure is dangerously high?
That's where a counter-hormone called atrial natriuretic peptide, or ANP, comes into play.
And this one originates in the heart, right?
Yes. When your blood volume is too high, the physical chambers of your heart are stretched by the excess fluid. The stressed heart muscle cells release ANP into the blood.
And what does ANP do?
ANP travels down to the kidney and acts as the direct physiological antagonist to the RAAS system. It tells the kidney to shut down the sodium pumps and flush the excess salt and water out into the urine.
It's a built-in thermostat. RAAS is the heater, constantly firing up to retain fluid and build pressure when things get low. ANP is the air conditioner, kicking on to flush fluid out when the pressure gets too high.
It's a beautifully calibrated push and pull.
Beautifully calibrated, yes. Until human behavior aggressively overrides it, which is where things become extremely dangerous.
Yeah, that's where the real-world application gets scary.
This is where the deep dive gets incredibly practical. Because when we misunderstand how these hormonal gates work, the results are catastrophic. Let's talk about exercise-associated hyponatremia. The sources highlight this as a major failure of sports science communication.
For decades, the golden rule hammered into marathon runners and athletes was drink as much water as possible. The fear of dehydration was absolute.
Right. Carry a water bottle everywhere.
Exactly. But that advice completely ignores the physiological reality of how ADH functions. We tend to think that a dry mouth or the feeling of thirst is our body's primary defense against dehydration.
But thirst is actually a lagging indicator, isn't it?
A very late indicator. Your brain's salt sensors are so incredibly sensitive that they start dumping ADH into your blood when your osmolality shifts by just 1 to 2%.
Wow, that's small of a shift.
Yeah, you don't consciously feel thirsty at all yet, but your pituitary gland is already screaming at your kidneys to lock the aquaporin gates and conserve water.
And imagine you are running a marathon. You're 3 hours in. You are sweating. Your muscles are breaking down. Your body is in a state of massive physiological stress. The sources note that physical stress itself causes your brain to dump even more ADH into your system.
Right. Your body is chemically barricading the exits. Because your ADH levels are so high during intense exertion, your kidneys hit a hard physiological ceiling.
What's the limit?
They max out at being able to excrete only about 800 milliliters to maybe 1 liter of urine per hour. The aquaporins are locked open to reabsorb the system, simply cannot get rid of free water fast enough.
So if you follow that old 1990s advice, And you are aggressively chugging 1.5 liters of water at every aid station because you're terrified of cramping what happens to all that excess water.
It has nowhere to go but into your bloodstream. And because you are adding pure water to a closed system, you aggressively dilute your blood. Your sodium levels plummet.
That's a state called hyponatremia.
Exactly. And because your blood is suddenly so watery, osmosis forces that excess water out of the blood and into your body's cells, causing them to swell.
And when that happens to your brain cells inside the rigid, unforgiving bone of your skull, it is fatal.
It's incredibly dangerous.
This is exactly what happened in the tragic case of Cynthia Lucero at the 2002 Boston Marathon. She was a 28-year-old runner who followed the conventional advice to hydrate aggressively. She drank copious amounts of fluid, her blood sodium collapsed, and she died from exercise-induced brain swelling.
It is a devastating example of well-intentioned advice running headfirst into an inflexible biological wall. That tragedy, and others like it, forced global sports medicine bodies to massively rewrite hydration guidelines.
From drink as much as possible to what?
They had to pivot away from drink to stay ahead of your thirst to the much safer drink to thirst. It highlights a critical clinical reality in the acute setting of an endurance event. Overhydration can actually kill you much faster than dehydration.
And this precarious balance with sodium doesn't just happen to marathon runners. It is a daily high-wire act in hospitals, too.
Oh, absolutely.
Let's say you bring a patient into the ER, and their blood work shows chronically low sodium. My first instinct would be to hook them up to an IV of heavily salted fluid and just drive that number back up to normal as fast as possible, fix the spreadsheet.
If you do that, you will likely cause irreversible brain damage. It causes a condition called osmotic demyelination syndrome.
Why does that happen?
You have to remember that human cells adapt. If a patient has had low sodium for days or weeks, their brain cells have actively pumped out their own internal particles to match the dilute blood, specifically to prevent themselves from swelling. They've found a new, fragile equilibrium.
So if you suddenly flood their bloodstream with a high salt 4-up,
The rapid shift in osmosis violently sucks the water back out of those adapted brain cells. They shrink so rapidly and severely that it destroys the myelin sheath, the vital protective insulation wrapped around the neuron. It's like violently stripping the rubber casing off live copper wires in the brain.
which is why the medical sources place a strict physiological speed limit on doctors. They are legally and medically capped. They cannot safely correct a patient's sodium levels by more than roughly 8 to 10 milliequivalents per liter over a 24-hour period.
Right, you have to tiptoe the system back to normal to give the brain cells time to readapt.
Now, speaking of adapting to sodium, if we pull back and look at the public health data in our sources, we run into one of the most fiercely contested battlegrounds in modern nutrition.
Yes, the great dietary sodium debate.
And looking at these conflicting papers, I feel like we are stepping on a nutritional landmine here. Just to be absolutely clear up front to you listening, we aren't taking a side in this fight today.
Precisely. We are merely reporting the controversy from the sources. We aren't endorsing any specific nutritional view.
We are purely looking at the physiological arguments both camps are making in the literature.
Exactly. On one side, you have the mainstream consensus from bodies like the American Heart Association and the World Health Organization. They advocate for strict limits on daily dietary sodium.
And their rationale is built squarely on the RAAS system we just walked through, right?
Yes. They argue that excess dietary salt stays in the blood, pulls in water via osmosis, permanently expands your blood volume, and subjects your blood vessels to chronic high pressure, leading straight to heart attacks and strokes. It is a very direct, linear, mechanical view.
But then you look at the dissenting researchers in these sources, and they are pointing to large population studies that show a J-shaped curve.
Right, the J-shaped curve.
Their camp argues that, yes, incredibly high sodium is dangerous, but severely restricting sodium is also correlated with worse cardiovascular outcomes.
Their physiological argument is that if you artificially starve the body of sodium, the kidney panics. It kicks the RAS system, the renin, the angiotensin, the aldosterone into a state of chronic screaming overdrive to desperately save whatever salt it can find.
Stress hormones are just constantly elevated.
Exactly. And they argue that having those stress hormones constantly elevated damages the heart and blood vessels more than moderate salt intake would. They believe the broad public health messaging completely ignores the kidney's highly adaptable hormonal feedback loops.
It is a fascinating ongoing war in the literature. But what isn't debated in any of these papers is how vulnerable the system becomes when it starts to fail, particularly in the elderly.
Yeah, aging really changes the equation.
As we age, two things happen simultaneously. First, Our brain's salt sensors degrade, meaning our conscious sensation of thirst becomes heavily blunted. We simply forget to drink.
Right.
Second, the kidneys' loops and nephrons lose their efficiency. They can no longer concentrate urine effectively.
It's a double physiological failure. You have an aging kidney leaking water because it can't concentrate the urine, and an aging brain failing to trigger the thirst mechanism to replace it, which makes fluid management in geriatric care incredibly complex and dangerous.
So when we trace the journey of a single drop of water through the body, we realize it is subjected to an astonishing gauntlet of checks and balances.
It really is.
Fluid control isn't just about water trickling down a pipe. It is fundamentally an active, aggressive process of reabsorption, governed by a delicate push and pull of powerful hormones, ADH, RAAS, and ANP. And whether you are a marathon runner, an ICU doctor managing an IV, or an aging adult, misunderstanding how those hormones behave has profound consequences.
It really does change how you view your own anatomy.
But I know you were looking at the clinical outcomes in these papers, and you had a final thought on where all this physiology leaves us today.
I did. When we look at advanced chronic kidney disease, this entire magnificent system we just described eventually fails. And to save those patients, we rely on external dialysis machines.
Which are lifesavers.
Oh, dialysis is an absolute miracle of modern medicine. It saves millions of lives. But fundamentally, a dialysis machine relies on simple passive diffusion across a membrane. It filters waste based on concentration gradients.
So it's basically the 19th century view of the kidney.
Exactly. In a very real way, our most advanced artificial life support is essentially functioning like that 19th century idea of the kidney as a passive sieve.
Wow.
And given that our natural kidneys dedicate a massive 25% of our resting oxygen to actively run this furious 180-liter filter and reclaim operation, it raises an important biological question.
What's that?
Will future artificial kidneys ever be able to genuinely replicate that high-energy, high-precision active transport? Or will artificial medicine always be trapped trying to replicate the kidney as a simple, passive filter?
That is a staggering thought to end on. The sheer biological engineering required to build a machine that does what your kidneys are doing effortlessly right this second is almost incomprehensible. Next time you drink a glass of water, just remember your kidneys are not a coffee filter. They are a high-stakes, 180-liter-a-day recycling plant burning immense amounts of energy to keep you in a state of perfect balance. Thanks for joining us on this deep dive, and as always, keep asking questions and stay curious.